Welcome to this overview of infrared thermography technology, the technology that actually allows us to see heat without requiring machinery shutdown. This program answers questions about the theory of heat and infrared thermography, how scanning systems work, typical applications, and considerations for using this growing technology. Because heat, or the lack of it, can indicate emerging machine and equipment problems, infrared thermography can detect faults that elude other predictive maintenance technologies. Infrared thermography can be used to detect faults such as poor electrical connections in splices, steam leaks, temperature fluctuations in processes, cold spots in paper machine dryer rolls, valve or injector malfunction, overheated bearings, leaking seals, refractory breakdown, building energy and heat loss, built-up roof leaks, and problems in transformers, distribution panels, motor stators and rotors, as well as determining levels in tanks. In the field of thermography, a fault is usually referred to as an anomaly or nonconformity. That is, it doesn't meet the standard. The list of faults then could be called a list of anomalies. In order to get the most from infrared technology and determine whether an application will be effective, it is necessary to understand the theory behind it. The infrared technology measures the heat or radiation from certain wavelengths of the electromagnetic spectrum. The visible light, or colors we see, are only a part of the same electromagnetic spectrum. The prism separates light into its distinct frequency bands and shows the color range for the band. Actually, there are many more wavelengths, but these are the ones visible to the naked eye. These other electromagnetic waves were discovered in 1800 by Sir William Herschel, Royal Astronomer to King George III of England. While using a blackened thermometer to measure the temperatures of each color of the spectrum produced by the sunlight passing through a prism, he noticed that the temperatures increased well past the area of the visible spectrum before dropping again. He referred to this range of the spectrum as the thermometrical spectrum. The term infrared was coined about 75 years later. Infra meaning below or the area immediately below the red area of the spectrum. Beyond infrared is the region of microwaves, and then the radio waves, the UHF, VHF, and the ULF. At the other end of the visible spectrum is the color violet. The wavelengths just above violet are referred to as ultraviolet. Above that are X-rays and then gamma rays. Over the course of time, special sensors have been developed that are particularly sensitive to electromagnetic waves in the range of infrared, which is from 0.75 microns to 1,000 microns or 1 millimeter. These sensors or detectors are incorporated into special cameras so that infrared images can be viewed and continuously updated in real time. The first of three primary sensor types is the pyroelectric Vidicon. It uses a vacuum tube with crystals as its sensor. Movement activates the crystals and causes them to stand up, allowing the electromagnetic waves to pass through, producing an image on the rear of the tube. One characteristic of the crystals is they stand up only momentarily when movement is detected. For non-changing images, a chopping of the scene must be performed or the image will fade out. A second type of detector is the single-element detector. This detector is similar to the CCD chip in a video camera. As the infrared energy strikes the detector, an electric output is generated and the scene is produced. These chips can be sensitive to either the short or long waves of the infrared energy. The third type of detector is the focal plane array. It is actually many single-element detectors working in unison. Since the chips are very small, they can be mounted on a surface with, say, 512 high by 512 across. The area can have as many as 2,000 by 2,000 or 4 million chips acting in unison. An array of chips produces the highest quality image of all the infrared cameras on the market. Many of the detectors used in a single element or focal plane array must be cooled to obtain the response needed to provide a high-resolution image and accurate temperature measurements. The cooling can be through a compressed gas, liquid nitrogen, a Stirling closed cycle cooler, or thermoelectric cooling. Whatever the cooling method, a consistent temperature in the camera must be maintained for the best accuracy. The signal generated by any of these detectors is typically converted into a video signal so the image can be viewed on a monitor or recorded onto videotape. This allows storage of these images for later comparisons or reporting. Choose the camera that produces the best image and it fits into your budget. Remember that higher cost does not automatically equate to a better quality image. The goal of a thermographer is to detect heat differentials and determine specific temperatures. With a good quality camera, temperatures can be determined within 1/10 of a degree. The camera system we are using here, and for most of the images used in this program, is the CSI Model 9000 thermography camera. It uses a thermography camera with the focal plane array technology, which can be used as a standalone unit. This system uses 3 other components that are needed primarily for documenting and reporting. The 8mm video camera provides a visible picture of the scanned equipment for comparison and recognition. Signals from both cameras are sent to this miniature color video recorder, where the infrared image or visible image can be displayed and recorded. An electronic pin-based computer provides a means to write any notes, which will then be stored with the image and downloaded to the computer. Whatever system you use, there are certain considerations that must be made in order to make accurate temperature measurements. Remember that the infrared camera is used to look at objects that may be hot, cold, or near ambient temperature, and that it actually views the radiated energy. This radiated energy can be real and provide an accurate representation of the object. However, the radiated energy can be reflected from another source and provide invalid images and temperatures. To illustrate this, let's use 3 cans that are each marked with several colors of tape. The first can will fill with hot water. The second can will leave empty, and the third can with ice. And cold water. Here the colors of tape are clearly evident using a normal camera that is sensitive to the visible light. Now the viewing screen is split, showing the visible light on one side and the infrared image on the other. Although the infrared image can be displayed in color, where the brightest or whitest spots indicate the hottest temperatures, most seasoned thermographers use a grayscale or black and white image to more accurately determine the levels of brightness. Here we are using a grayscale image, where the hottest temperatures are lightest and colder temperatures are progressively darker. So the hot can appears light and the cold can is dark. The empty can is some temperature between. All the tapes appear to be the same color for each can because they are actually the same temperature as the can. On the back of each can, however, are 3 more tapes. One is gray, one is white, and one is silver. In the normal light-sensitive camera, these colors appear distinct. The infrared image also clearly shows one tape on each can is different from the others, which indicates a temperature difference. On the hot can, the silver tape appears to be colder than the other tapes. On the cold can, the silver tape appears to be the hottest. What causes this? Are the silver tapes actually a different temperature? The tapes on a can really are the same temperature, but let's look at them more closely to determine the cause of the apparent temperature difference. Notice that the white and gray tapes appear the same color or temperature, and they both have the same textured surface. However, the silver tape has a smooth or reflective surface. This reflective surface is actually reflecting the ambient temperature of the room, or background temperature, and therefore does not radiate or emit the true temperature. Every object differs in the way it emits the true heat or infrared energy. This emitting is called emissivity and is a unit of measure which can be thought of as an efficiency factor. Determining the emissivity of an object is the first consideration in thermographic imaging. All objects are rated on their emissivity. A perfect emitter has a value of 1 and is called a black body. In the real world, there are no perfect emitters or black bodies, but all objects have a fractional value and are called gray bodies. Manufacturers furnish a table of emissivities for various materials. This table shows emissivities of some common materials. With one being a black body or perfect emitter, notice that human skin has a value of 0.98 or 98% of the value of a black body. Iron oxide has an emissivity of 0.89, and lower on the scale are rolled sheet steel, building brick, cast iron, and polished aluminum. All objects have some reflectivity as well as emissivity. Mathematically, a perfect black body has an emissivity of 1, or E equals 1. All gray bodies must account for both emissivity and reflectivity, so the equation now is 1 equals E plus R, where E is emissivity and R is reflectivity. In our example of the cans with the tapes, the silver tape is the same temperature as the others, but its reflectivity causes it to appear as another temperature. Since the reflectivity affects the emissivity, the camera must compensate for the reflective background in order to obtain the accurate temperature. Other characteristics of some materials must be considered when making accurate temperature measurements. To illustrate, we will again view the cans, but put a piece of thin dark plastic over the lens of both cameras. The visible light image is black, but the infrared camera produces a clear image of the cans. Why doesn't the camera see the plastic film? If the plastic is doubled, the image of the cans is still evident, although somewhat diminished. Doubling the plastic again causes the image to be darker still. Each time the plastic is doubled, less of the image is apparent. That is, less of the infrared energy is transmitted through it. Like emissivity, this transmitted energy must be compensated for in order to produce accurate temperature measurements. Now the formula must include this transmitted energy, so the complete formula is 1 equals E plus R plus T, where E is emitted energy, R is reflected energy, and T is transmitted energy. There are only a few objects that transmit infrared energy, but most are opaque, so that usually it is not necessary to compensate for transmitted energy. This allows us to adopt the simpler formula of 1 equals E plus R. Some objects have surprising characteristics. Let's use this sheet of glass, for instance. When it is placed in front of the cameras, the visible light energy is transmitted easily, but the infrared energy is substantially decreased. Sheet plastics like plexiglass are very similar depending on the thickness and chemical makeup. This means that when scanning from an aircraft, one of two things must occur. The door or window must be opened, or the camera must be mounted outside the aircraft cabin. When performing a thermal scan, there may be times when the area to be scanned is not accessible. In these cases, a mirror can be used, and then the reflected energy can be measured. Most mirrors have the reflective surface behind the glass, though, which causes the energy to be transmitted through the glass twice, once going to the reflective surface and once coming back from the reflective surface to the camera. We have already determined that glass does not transmit infrared energy well, so this would not provide an accurate temperature. The solution is to use a mirror called a first surface mirror, which has the reflective surface on the front side of the glass. This first surface mirror allows the infrared energy to reflect the energy emitted from the object and provide an accurate temperature measurement. Other considerations must also be made to determine accurate temperature measurements. Because thermography is the plotting or graphing of heat energy, we need to understand some principles of heat and its movement, or thermodynamics, in order to determine the effects on heat measurements. A law of thermodynamics says that heat will move to regions of cold until the temperature is at a state of equilibrium. The greater the temperature difference, the faster the heat transfers. Actually, there is no such thing as cold. Cold is only the absence of heat energy. There are three ways that heat moves from one area to an area of less heat. One way is conduction, that is, the heat transfers through a solid. An example of this is the heat from a stove eye heating the bottom of a pot first, and then gradually heating the sides. In industry, an example would be a bearing overheating and then heating the surrounding housing and the piece of equipment, or heat generated from a loose electrical connection heating the wire for a distance. The second method of transferring heat is called convection. Convection is the transfer of heat through a liquid. Whenever we think of liquid, we think of water or some other fluid. However, air is also considered to be a liquid. A typical example is the cooling system in an automobile. The heat from the engine is transferred to the liquid coolant. The coolant is then pumped through a radiator where air crosses the radiator, transferring heat to the air, which leaves the liquid coolant much cooler. The third method of transferring heat is called radiation. The biggest source of radiation in our world is the sun. It emits or radiates heat energy, and every object this heat energy strikes either absorbs or reflects it to some degree. In industry, it is the source of this heat transfer, or radiation, that we want to view and measure with our thermography technology. The next few sections illustrate measuring the radiated heat from various sources and recommend steps of action that help avoid making wrong measurements. Thermography in industry today is most often used for detecting electrical anomalies. Common applications include electrical panels, splices, cable trays, junction boxes, phase balancing, overloading, as well as transformers, switch yards, and even transmission lines. The first and major consideration when scanning electrical equipment is safety. Always use extreme caution and make sure the personnel with you are qualified and familiar with the equipment to be surveyed. Besides safety, there is another consideration that should be made when scanning for electrical faults. Most electrical circuits are designed to operate at 80% of the capacity. This allows a conservative temperature rise, which is still well within the safety margin. When the load or current draw is less than 80%, the temperatures and the current may be carried across poor connections or even a wire that has broken strands without heating excessively. Perform your scans while the electrical system has at least a normal current load. Avoid scanning at reduced loads. When scanning closed panels, some may appear to be hotter than others. But remember that you are to determine the source of heat. Is this really radiated heat, or could it be reflected heat? If you can visibly see a bright spot or reflection, it will cause a thermal pattern. Is the heat from the cover itself, or has it become hot due to conduction or convection of internal heat? Have qualified personnel open the box for better inspection. Depending on the type of panel, there may be large lug connections, fuses, breakers, or a throw switch. When connections of any type are loose, heat is generated because loose connections cause electricity to jump or arc across the joint. Arcing heats the joint and can cause pitting. Another reason for the excessive heat is that the loose connection acts similar to a wire or cable that is sized too small for the load. It is attempting to carry more electricity than the touching surfaces can allow. Excessive heat is generated when a lug is not tied on the wire, or a fuse is not tied in the holder or any other connection. There is usually some general concern for splices that are made in cables and should be checked for hot spots. The excessive heat generated by any loose connections can cause hot spots, overheat wires, which breaks down the insulation and can cause other shorts in the system. When a loose connection is suspected, it is important to pinpoint the exact location. If the entire area is bright or hot, turn down the iris on the camera until only the hottest point is bright. This will be the exact source of the heat and most likely the location of the loose connection. A wire or cable that has too much load can be confused for a loose connection. One way to distinguish between the two is an overload tends to heat the entire length of the wire, while a loose connection is localized and generates a hot spot. These additional examples of various overloads and loose connections illustrate the difference. Notice how some wires are hot their entire length, indicating an overload, and others cool down over a short distance. Stranded wires or cables can have a break in some of the strands, which forces the load to be carried on the remaining strands. When this occurs, the good strands are usually forced to carry too much current and cause excessive heat. The broken strands will be much cooler, and the thermal image will appear as barber pole striping or candy striping. Loose connections, overloading, and broken strands each have their own unique characteristics, which can be distinguished in a thermography image. Whether the temperature is within tolerance or even measured may not be of any concern here. The fact that there is an anomaly requires action. When scanning a panel or junction box, the temperatures may all be within tolerances. There are no